This video is all about performing basic vector operations, but doing it in component form. We have been doing a lot of things in graphical form, so like drawing arrows and using that method to determine like the sum of vectors. And now we're going to do it in component form. And the reason that we want to do it this way is that it really is the safest way to add vectors or perform basic operations if possible, because you no longer have to worry about keeping your vectors like perfectly to scale and drawing them perfectly and measuring their lengths, that type of stuff. It's difficult to do. So component form is usually the method of choice when you're really trying to add vectors or subtract them or perform any other operations. You're probably going to put them into component form and then do it that way. And it actually is pretty intuitive. If you are familiar with basic algebra, you know that you can't combine terms if they have unlike variables. A lot of the same principles are going to carry forward whenever we're working in component form. So the first basic operation we'll talk about is scalar multiplication. This is when you multiply a vector by a scalar. Scalar multiplication is distributive. So if there is a scalar, I'm calling this alpha, out in the front of some parentheses, that scalar gets applied to all of the vectors. So even if the vectors already have scalars being multiplied by them, you just do it regular, like just kind of like regular math here. You combine the scalars out in front and you multiply them by the vector. Scalars are just like numbers, so just treat scalars just like any old number that you've dealt with before. The scalar multiplication is still distributive even when you're doing things in component form. Addition and subtraction, still very similar to regular math. It's commutative, so a plus b is the same thing as b plus a. Same thing with vectors. Vector a plus b is the same as vector b plus a. Also with subtraction, you can think of subtraction as the same thing as adding, but with a negative sign in front of the term that you're subtracting. So like a minus b is the same as a plus -1 times b. So same thing with vectors. Vector a minus vector b is going to be vector a plus -1 times vector b. The thing that's a little bit additional here is that when you're doing things in component form, you'll have some terms that have like x hats in them, some terms that have y hats, some terms that have z hats. Just be careful that when you're adding vectors and they each have their own vector components, you can combine vector components if they have like terms. So like in this example here, I see this term and that term. I have 5x hat plus 4x hat. I can combine those terms. They both have x hats in them. So on over here, I've simplified that. 5x hat plus 4x hat is 9x hat. This y term, I have -3y hat. There's nothing to combine that with. That one stays by itself. So -3y hat shows up on the other side of that equation. Then I have -4z hat plus 9z hat. I can combine those terms because they have like vectors. So -4z hat and 9z hat, that comes out to +5z hat. So very similar to basic algebra that you're already familiar with. Just make sure you're only combining terms that have that are like terms. Some other vector operations that we will get into is the dot product. It's actually so important. I'm going to devote an entire lecture just to doing the dot product in component form. It's really, really important you can do that correctly because we've already seen how often we use the dot product to extract vector components, to find norms. It's a really important operation. We're going to talk about that in detail to make sure you're doing the dot product correctly in component form. And then dividing by a vector is still not allowed. You could never, ever, ever divide by a vector, even in component form. So don't try to do it. Let's do a couple examples just to make sure that we're all familiar and comfortable with doing things in basic operations in component form. I have two vectors right here, a and b, and I want to find vector m, and I've defined vector m as 2 times a minus 0.5 times b. So let's figure out those two things first, and then we'll find vector m. So let's find 2 times a. Well, that's just going to be 2 times all of the component form of vector a. So I'm going to say 2 times 3x hat plus -2y hat plus -9z hat. I'm going to distribute that scalar, the number 2, into that vector, the component form of vector a. So I get 6x hat plus -4y hat plus -18 z hat. That is the result of 2 times a, vector a. Now let's find negative 0.5 times vector b. That's going to be negative 0.5 times negative 8x hat plus 18y hat plus 2z hat. Again, distribute that scalar, the negative 0.5. Be real careful with your negative sign. So negative 0.5 times negative 8 is positive 4x hat. Now I have negative 0.5 times 18. That'll give me negative 9 y hat. And then negative 0.5 times positive 2, that is going to be negative 1 times z hat. You don't even have to write the 1 in there. If you just want to write negative z hat, that's fine. All right, so I have those two pieces of my puzzle. Now I'm going to combine them. I want to find vector m, which is going to be 2a hat, or sorry, vector a, 2 times vector a, plus negative 0.5 times vector b. So I can combine these two vectors that I've written in component form. So I have 6x hat plus negative 4y hat plus 18z hat. And to that, I am going to add my negative 0.5 times vector b, which I've already found down here. I have 4x hat plus negative 9y hat plus negative 1z hat. And now I wrote my vectors, I kind of stacked them on top of each other. That kind of helps me visually to only combine terms that have x hats together and y hats together and z hats together. You don't have to write it like this. You could write one big long horizontal equation. I'm just kind of showing this to make sure that we only combine like terms. So as far as x hats are concerned, I see 6x hat plus 4x hat. So that gives me 10x hat. Now I see negative 4y hat and negative 9y hat. That gives me negative 13y hat. And I see 18z hat and negative 1z hat. That gives me a positive 17z hat. And that is my final answer for vector m in component form. All right, let's do one more example. This one, we're going to kind of see two versions. We're going to do this problem graphically, this old method that you were first taught when we first started talking about vectors. Then we're going to do it again, but in component form. And we're going to get a little bit of extra practice of putting vectors into component form. You had a little bit of practice with this, and now we're going to do another example with actually putting a vector into component form and then performing basic operations. So first, let's do it graphically. We have two-dimensional vectors. So these vectors live in the plane of the board or the plane of your computer screen, however you want to think about it. We are going to add them graphically. That's the tip to tail method of vector addition. We're going to find the resultant. Then we're going to put the vectors into component form and add them in component form. And we're going to compare our answers and see if they agree with each other. So let's do the graphical method first. Remember, graphically, you take the vectors that you're adding together and you add them tip to tail. So here's vector f. I'm just going to move it down here, translate it. I'm going to add vector t so that the tail of t is starting at the tip of f. Then I connect the beginning point, so the tail of f, to the tip of t. That is my resultant. Notice that the resultant is not tip to tail. It is tail to tail and tip to tip because it is the sum. So vector r equals f plus t. So that is vector r right there. You can kind of see, you can get a general feeling for the length of vector r. It looks a little bit bigger than t, pretty close though. And it's kind of pointing down and to the left, slightly below the horizontal. So that's what we get graphically. That's what vector r looks like. Now let's do some work and put it into component form. So each of our two vectors we're going to put into component form first. So the way that we do this is we draw our vector. So let's start off with vector f. And I am going to draw it tail to tail with our unit vectors for this system. I've already chosen a coordinate system for this problem. So I'm going to draw these vectors tail to tail with this vector f. So y hat is pointing to the right, z hat is pointing up, and x hat is coming out of the board. And now I am going to identify alpha, beta, and gamma. Those are the angles that this vector makes with each of the unit vectors. So in this case, alpha is the angle that this vector f is making with the x hat unit vector. X hat is coming out of the plane of the board. That makes it automatically 90 degrees to anything that lives in the board. So alpha is 90 degrees in this particular problem. Beta is the angle between vector f and the y hat unit vector. So this angle here is angle beta, and it is conveniently already labeled for us. That is 120 degrees. And gamma, that is the angle between our vector f and the z hat unit vector. So I would say this one here is angle gamma. And I typically choose the smallest angle between those two vectors. So that's why I went in the counterclockwise direction here. I just choose the smallest of the angles between z hat and f. So I'll do a little bit of work to get that one. I see that angle gamma would be 180 minus 120 plus 90 degrees. So I'm adding this little piece right here. That's 180 minus 120. That's 60. And to that, I'm going to add this 90 degrees right there. So angle gamma is 60 plus 90, which is 150 degrees. So I've identified my three angles. Now I'm going to put it into that generic expression for a vector. So vector f is going to be the norm of vector f times cosine alpha, and that gets multiplied by x hat, plus the norm of vector f times cosine beta, all of that times y hat, plus the norm of vector f cosine gamma z hat. All right, let's plug in our numbers. The norm of vector f is 13.17 newtons times the cosine of alpha, that's 90 times x hat. Plus now the y hat term, 13.17 times the cosine of 120 times y hat. And now the last term, I have 13.17, don't forget your units, that's newtons, cosine of 150, that's gamma, all of that times z hat. So I can plug in some numbers and simplify this expression. Vector f in component form, I know the cosine of 90 is 0. So this term right here, that very first term, is going to disappear. It actually is 0 because the cosine of 90 is 0. So I'll do 13.17 times the cosine of 120, and I get negative 6.585 newtons y hat plus 13.17 times the cosine of 150. That's negative 11.4 newtons z hat. So that is the component form of vector f. We're halfway there. Now let's do the same thing. Let's do it for vector t. This would be a good chance for you to pause the video and see if you can put vector t into component form and then check your answer with me. So I'm going to keep going, but I recommend pausing and doing this part on your own and checking to see if you can do it correctly. So I'm going to redraw vector t on this page. Let's identify, I'm going to redraw my unit vectors tail to tail with vector t. Now I'm going to identify alpha, beta, and gamma. So alpha in this case, again, it's 90 degrees because unit vector x hat is coming out of the board and vector t lives in the board. So they are automatically 90 degrees from each other. Beta, that's the smallest angle between vector t and the y hat unit vector. So I would say angle beta is this angle here. So angle beta would be 90 degrees minus 73 degrees. That'll give me this little piece right there. And then I'm going to add another 90 degrees onto there to account for that little piece right there. So that's angle beta is 90 minus 73 plus another 90. So I would say angle beta is 107 degrees. And now angle gamma, that is the angle between vector t and the z hat unit vector. So this one right here, that little piece right there, that's angle gamma, which is 90 minus 73 degrees, which is 17 degrees. Whenever you're doing this method, you really need to look at the picture and identify each of these angles. There's no like prescription I can give you that gamma is always 90 plus this or anything like that. You always have to look at the picture and identify these angles and use some basic geometry to figure out any missing little pieces of angles that you don't know. All right. Vectors t's norm was 8.89 newtons. I'm going to need that when I put this into component form. All right, let's put vector t into component form. Vector t using the generic prescription of a vector. Vector t is equal to the norm of vector t times cosine alpha x hat plus the norm of vector t cosine beta y hat plus norm of vector t cosine gamma z hat. Let's plug in our numbers. Norm of vector t was 8.89 newtons, cosine of 90 degrees times x hat, plus norm of vector t, 8.89 newtons, cosine of 107 degrees, all of that times y hat, plus 8.89 newtons, cosine of 17 degrees, and all of that times z hat. All right, let's simplify. I know this first term is going to go to 0 because the cosine of 90 degrees is 0. So that first term is gone. The next term, 8.89 times the cosine of 107, that is negative 2.60 newtons y hat. And then my last term there, 8.89 newtons times the cosine of 17, just cosine of 17, that is 8.50 newtons z hat. So there is vector t in component form. So now let's find vector r in component form. Vector r was vector t plus vector f. So I'm just going to copy down what our answers were in component form for vectors t and f. Vector f was 6.585. All right, so those were our two vectors in component form. Let's add them together. Negative 2.6 plus negative 6.585. I get negative 9.185 newtons y hat plus positive 8.5 plus negative 11.4, I get plus negative 2.9 newtons z hat. So that is my expression for vector r in component form. Let's compare this to the graphical representation that we got from the graphical method. If you look at our vector r in that case, it kind of looked something like this. It's pointing down and to the left. It looked like it had a norm, slightly bigger than t, but kind of close to it. If you look at our vector r, and based on our coordinate system, we said y hats were going to the right and z hats were going up. If you look at our component form, I see that it has a negative y hat component and it has a negative z hat component. That is consistent with the picture that we have for vector r. It's pointing down and to the left. So that's consistent with that picture. And you can notice from our component form, the y component is a lot longer than the z component. So that horizontal component is a lot longer than the vertical component. That is also consistent with our picture. So it looks like both of our methods agree with each other. We have done things correctly.